Hello everyone, I'm Chen-Feng Wei, a PhD student from the University of Manchester. In this video, I'm presenting our work on ESBMC version 7.7, a verification tool that now supports automated branch coverage analysis by using CFG-based instrumentation and SMT solving. So this project is a collaborative effort by our team from several institutions. I would like to acknowledge all the co-authors here who helped to make this work possible. So for those who may not be familiar with our work, ESMC is an open source boundary model checker designed for verifying C and C++ programs. We have participated in SBCom and TestPong competition for many years, and ESMC has shown good results in terms of bug detection. However, we have never participated in TestCom's cover branches category due to the lack of branch coverage analysis and automated test suite generation. So basically, there's a gap here. We want to find a method to leverage the power of this advanced verifier to be able to perform also coverage analysis. So to bridge this gap, we present ESBMC version 7.7 with two main contributions. First, we propose an instrumentation algorithm to simulate the behavior of entering a branch. That is, even if a program enters the branch body, it must satisfy the guard condition. So what we do here is convert this guard condition to a property assertion, and we add it back to the source program. And the next step is that's how we verify this instrumented assertion. Because before version 7.7, EFNC could only identify and report the first founded violate program or property, even if there are multiple violate property within the program. So we need to find a way to like EFNC to support verify multiple assertions. Additionally, we use an incremental reasoning method, that is k-induction. This allows us to automate and soundly verify all the instrumenting assertions. Here is the framework of our work. As you can see here, we have the input C program, and we convert it into a ESBMC internal representation. And at this stage, we perform our instrumentation. So after we instrument it into this intermediate representation, we send it to backend, perform symbol execution and slicing, and do the SMT solving. Given the SMT solving results, we introduce a test case generator to generate test suits correspondingly. So the first stage is how we perform instrumentation. This is mainly taking place in the front end and middleware within ESBMC. So basically, we applied our algorithm upon the go-to program, which is the intermediate representation of EMC, and it's virtually identical to the control flow graph. The reason we perform on this other than the source code level is because that in this go-to program, all the control flow structs like if else, while, for, switch cases are all normalized into the if go-to blocks. So this normalization makes our instrumentation more uniform. So here is an example to show how we perform this simplification. On the left-hand side, a simple example. You can see we have while, if, and else if. So we convert it to the go-to program, and ENC has an option to convert it back to the C program. So on the right-hand side, it's the converted C program, and we compare it. You can see that the while and else if are all simplified to the if go-to. So after the simplification, we can now focus on the if statement only. So to enter a branch guarded by the condition like if con, there must exist an assignment that satisfies this con, which is equivalent to checking if there's a counterexample that satisfies the assertion with negated condition. So for each conditional branches, we insert two assertions before it to model the true branch and false branch. Here is an example. That's how we do it. So before each if statement, we inserted two assertions back to the go-to program. Additionally, since we are focusing on coverage and verifying the instrumented assertion, all the assertion that is irrelevant need to be ruled out. This includes the user-defined assertion in the source code and the safety checks assertion added by ESBMC internally. For example, in the source program, we have a verified assert. We convert it to a verified assert true, and we will slice it later in the slicer. Also, we disable the adding of the overflow check, as you can see here. The second stage is about how we solve the instrumental assertions, which need to be proven either correct or violated. This is mainly taking place in the backend of ESBMC. In the backend, we converted go-to program to verification condition, which is basically an SMT formula incorporating constraints that are assignments and assumptions and properties that are basically assertions. To enable ESBMC to perform multiple property verification, we split the overall property into units and assign each unit verification condition with an individual solver. Additionally, we are utilizing the power of incremental reasoning. Since ESBMC is a bounded model checker, it can only perform verification up to a fixed bound. In the context of branch coverage analysis, this stands for that some branches might remain unreached or unchecked during the analysis process. Even if we use a relatively large bound, we can still not guarantee that all coverage analysis is sound. Also, this might lead to state space explosion. To address this limitation, we introduced the incremental reasoning to collaborate with our multi-property verification. For example, for the bound K, we check that if the property holds up to this bound K, and prove that if we hold at K, it should also hold at K plus 1. So in ESBMC, this can be summarized in 3 steps. That is base case, basically the normal bounded model checking process, and forward reasoning by adding an assertion to prove that all the loops have been fully unwinded. And lastly, the inductive step to prove that if we hold at K, it should also hold at K plus 1. Here, we continue to use the previous example to demonstrate this incremental reasoning process. In the program, we have 3 if statements, and we have already added 6 assertion instances as branch coverage properties. By doing incremental reasoning, ESBMC will automatically increase the bound. So when the starting bound is 1, we have 3 instances got solved. Normally, this could be either correct or violated, but in these specific cases, they are actually found violated, means that these branches are formally proven to be able to enter. And since the coverage properties left, the whole process is continued. So we redo the slicing and regenerate the verification condition, and we redo the incremental SMT solving. And finally, since there's no property remains, the whole process terminated. Here is the result of ESBMC coverage analysis. As we can see, the whole verification process terminated at bound 4. All the true and false branches have been reached, thus the coverage is 100%. Lastly, whenever a property violation is found, we generate a test suite correspondingly. This is done by extracting the assignment from the output traces. And here is the result of our ESBMC cover branches category in the TestCom competition 2025. We ranked 7th and 8th among all participants. Here, ESBMC K induction and incremental apply similar incremental reasoning technique, but with some small tuning in terms of unwinding setting. And ESBMC is an open source project. If you are interested in our work, please do check our GitHub and official website. And thank you.